of a periodic table. What happens to the size of the atom as you move left to right? It's size decreases. Why does the size decrease? Because there's more protons that are pulling on the electrons, so it shrinks a little bit. What happens to the size as you go down the trends? Size increases because you're adding more, you're going into a new orbital, new energy level. Electronegativity. Where's the highest, strongest, most electronegative atom in the periodic table? It's up here. Fluorine, right? So electronegativity increases. Increases going up and to the right. That makes sense? So as you move across the periodic table, electronegativity increases, and as you go up, the electronegativity increases, and fluorine would be the strongest. What about ionization energy? What is ionization energy? Yeah, like the ability to pull an electron off. All right, so ionization energy is the same as basically electronegativity. All right, it's trends. So I'll say so ionization energy follows the electronegativity trend. Basically, the highest ionization energy would be fluorine. The lowest would be down here. And ionization energy is the energy required to pull an electron off an atom. Okay? So the smaller the atom is, the tighter they're held, the more energy it requires to take it off. The larger it is, the further away from the nucleus, the easier it is to pull an electron off. Okay. Okay. Electron configurations. So let's do what do we want to do? We'll do cadmium. Cadmium. Electron configuration for cadmium. We can use core notation. Okay? So you will need your data booklet. You will get a new data booklet for the test, for the exam. Here's my data booklet. There it is. Okay. So you have a periodic table. We are here. Cadmium. What's the closest noble gas to cadmium? Where is cadmium? Oh, there it is right there. So you go backwards to the nearest noble gas, which is krypton, right? So we don't have to write all the electrons leading up to it. We can just say krypton is our starting point. Then from there, we start here. Now, what is the first row, or so the first row for rubidium? Like, what orbital are we in? You're in the s orbital. Which number? 5. You just start counting. 1, 2, 3, 4, 5. And we fill up the first two, right? Because we got to go all the way to cadmium. So it's 5s2. 5s2. What's the next bit? Well, p's are over here, right? So it's D, right? And it's going to be 4D. And you got to fill them all up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 4D10. Kenzie. So 4D10. And that's it. Okay? I'm not going to ask you any of the ones where it's like, oh, it takes one electron from the S and it bumps it up and all that kind of stuff. I'm just going to look for a basic idea. Can you do the electron configuration of an atom? Also, I can also give you something like, if I say, what do I want to say? If I give you this, oh, sorry. AR 4s2 3d10 4p3. What atom is it? So 4s2 3d10 4p3. 4s2, and we're starting with argon. So go to argon. Come on, why are you not working? There we go. Argon is here. We go to the next row. 4s2 3d10, so we fill up all our d orbitals, and then it's 4p3. 1, 2, 3. Arsenic. Okay. I will give you something like that on a test. So I can give you both. I can give you cadmium, say what's the electron configuration, or I can give you the electron configuration. You have to tell me what the atom is. Okay? And all the little tricky ones, I'm not going to worry about those. We're just going to do the basics. Okay? Are we okay with that? All right. How many valence electrons are there? What do we worry about for valence electrons? What orbitals? P and S. So this one has 5 valence electrons. How many does this one have? It's only got 2. Okay. All right. I think we should do some Lewis structures because everybody seems to love Lewis structures, right? No? Nobody loves Lewis structures? Okay. There's 2 Lewis structure questions. So let's do H2S. So how do you do these? Does anybody remember how to do Lewis structures? What's the first thing you should figure out? Okay, ionic or covalent? Is this ionic or covalent? It's covalent. Okay. Valence electrons. Figure out the valence electrons. So, how many valence electrons does hydrogen have? It's got 1. How many does sulfur have? Sulfur. 1, 2, 3, 4, 5, 6. Right? Does that make sense? Because it's only s and p orbitals, so you just count the s and p. So hydrogen has 1, but we have 2 hydrogen atoms, plus the 6 valence means we have 8 valence electrons we have to account for in the bonding. Okay? How many bonds does hydrogen want to form? 1 each, right? So you want to draw it like that. Okay? Am I done? Why? You need to account for all the valence electrons. Every bond has how many valence electrons? 2. So I've got 4 valence electrons. I need 2 more. Now at the beginning, we would just put them like that, and that was fine. But I'm going to ask for the shape of the molecule. Okay, so lone pairs of electrons, where do they go? Think of water. Is water linear? No. So the actual shape of this is those lone pairs of electrons sit up top and they push the bond down. So this is bent. Okay. So I will ask for the the Lewis structure. Then I'll ask for the name of it, or the shape of it, sorry. So in this case, bent. I'm going to go through each one that I expect you to know. Bent. And then I will ask if it is polar or non-polar. So, is this polar or non-polar? It is polar, right? What is more electronegative, sulfur or hydrogen? Sulfur. So it's going to pull the dipoles like that. And because we don't have symmetry, due to the bent nature, this is a polar molecule. Okay. Let's do SiH4. What's the first thing you figure out? Valence electrons. How many valence electrons does silicon have? It's got 4. And hydrogen has 4. So we have 8 valence electrons. So Si, we have 4 hydrogens around it. Why doesn't hydrogen bond to itself here? Because if it bonds to itself, can it bond to silicon? No, because it only wants to form one bond, right? So silicon has to be at the center. Have I accounted for all the valence electrons? Okay. So the structure is good. What is the name of the structure? Right? It's tetrahedral. Does it have symmetry? It does. Therefore, it is nonpolar. What about CO2? Valence electrons. Carbon has 4. Oxygen has 6, but there's 2. So 16 valence electrons. How many bonds does carbon want to form? 4. How many does oxygen want to form? 2, right? Because oxygen wants 2 more electrons to get to 8. Carbon wants 4 more electrons to get to 8. So we get this. Is that the right structure? You get full marks for drawing that? Why would you not get full marks? Yeah. So we've accounted for 1, 2, 3, 4, 4 bonds. That's 8 electrons, but we need 16 valence electrons. And our oxygen wants 8. Right now it only has 4. So we put the extra dots there. Now you got all 16 valence electrons. What is the structure of this? What's the name of the structure? It's linear. Does it have symmetry? So it's polar or nonpolar? Nonpolar. All right. um, Carbonate. Figure out your valence electrons. 4 plus 3 times 6. We have 2 negative charge, so I have to add in 2 extra electrons, right? So that should give me 24. Yeah. 24 valence electrons. Carbon will be at the center. Carbon only wants to form 4 bonds. There's 8 electrons. There's all your electrons. Because it's a -2 charge, you should put it in brackets with a -2. And remember, that double bond can be on any of the oxygens. It doesn't have to be drawn like that. Okay? Do you remember what we call it when it has different structures? Resonance structure. Okay? I'm not going to ask you that, but does this molecule have symmetry? It does have symmetry. Because the double bond's moving around like super fast, right? Like I could draw it like this. or I can move it on to the next one. So you can think of it as being equally distributed. Okay. So I'll ask you again, does it have symmetry? So is it polar or nonpolar? Nonpolar. Okay. The molecule itself is nonpolar. Okay. Does anybody remember what this is called? Trigonal planar. So trigonal planar has symmetry. I'll show you the next one where it doesn't have symmetry. So this is called trigonal planar. Let me erase that because that doesn't even look like anything. And I'll show you how to tell if it has symmetry or not because the next one doesn't have symmetry. So if we do, I'll make it easy. NH3. How many valence electrons does nitrogen have? It's got 5. Hydrogen has 1, but we have 3 of them. So we got 8 valence electrons. There's 6, 7, 8. Okay, so there's your Lewis structure. Does this molecule have symmetry? No, because these electrons push the bonds down, right? So this is called trigonal 3 pyramidal. Pyramidal. And you know it's trigonal pyramidal if it has the lone pair of electrons. That's the difference between that one and this one. There's no lone pair of electrons here. Okay? So that's the difference. And so this is polar because no sim. All right? Yes, yes, yes. Okay. One final thing and then we're done. Bonding. Okay. So what are the types of bonds that we learned? That you have learned? So, well, okay, those are like a regular, just if I say a bond in a molecule, there's 3 types. There's metal, non-metal would be ionic. If you have ionic, well, let's say metal, non-metal. That's a transfer of an electron, right? The electron gets pulled away. You get transfer of an electron. And if you remember from that data table in your book, okay, perfect. These are the electronegativities. If we did sodium and chlorine, 3.0, 0.9, if you subtract them, you get 2.1. So the change in electronegativity difference is greater than 1.7. So if we did NaCl, what did I say? 3 and it's going to be 3.0 minus 0.9, 2.1. So if the electronegativity difference is greater than 2.1 or greater than 1.7, it's ionic. Okay? What other type of bond did we have? Polar. Which is a covalent bond. What's a polar bond? Unequal sharing of electrons. So unequal sharing of electrons. What was the delta En for that? Does anybody remember? Wow. The electronegativity difference was 0.2 to 1.7. Okay. So if we did carbon monoxide, CO, and you look at the electronegativities of carbon and oxygen, carbon is 2.5, oxygen is 3.5. One point zero is your electronegativity difference, which means you are polar covalent. In other words, the carbon oxygen, the oxygen pulls. I don't want to represent this. The oxygen pulls the electron density away from carbon. So you remember this, the partial positive, partial negative charges? It pulls more of the electrons away from the carbon. And then the final one was non-polar covalent, which is delta En, which is really small, is less than 0.2. But basically you see this in things like, I don't know, H2, where it's the same atom. It's a diatomic molecule, right? You get equal sharing of electrons. So this is equal sharing of electrons. Okay. I think I'm done. All right.